And y'all know y'all gonna need y'all's book, right? Huh? Well, everything, all number systems are numerical, so that would be right, but it's not what I'm asking for. We know a number system we call the decimal number system. We know it back and forth. We've been dealing with it since elementary school, right? So what we'll do is we'll start off looking at that and learning exactly what goes on in that number system so we can understand these other ones. Decimal number system, base 10, number system, scientific notation is different in binary than it is in base 10. So what's a K in decimal? How much is a K in decimal? 1K is equal to 1,000. Y'all know what a K is in binary? 1,024. Explain exponents, integer numbers. Everybody okay there? Y'all know what an integer number is? An integer number is a signed number without a fraction. Most Allen Bradley RS Logic 500 calls them integers. Most of your new PLCs call them real numbers. Fractional numbers, y'all okay with that, right? Real numbers no, I'm sorry. New PLCs call them real numbers. Allen Bradley 500 calls them floating point numbers. Yeah. Convert decimal numbers to binary and vice versa. Perform binary math. We're not going to worry about that. I'll show y'all that and impress y'all. But y'all not going to do you're not going to do math. Actually, binary math is easier than decimal math because on binary math you could carry up to binary math when you add most you're going to carry is a 1, right? And 1 plus 1 is 2. 1 plus 0 is 1. 0 plus 0 is convert binary numbers to hexadecimal and vice versa. So yeah, in binary, all we're adding is 1 or 0. I mean, multiplication is easy to me. Explain the octal number system, convert binary numbers. So we're going to deal with 3 number systems. We're going to deal with binary, decimal, of course. Let's make it 4. We're going to deal with decimal, which we should understand, right, pretty well. We're going to deal with binary, which is the only numbering system that a computer understands. We're going to deal with a numbering system called octal, which is probably only used in PLCs now. Computers have shifted up to a higher base number, and we're going to deal with a number system called hexadecimal. Now, what we use octal for, and then we're going to look at some codes that we need to understand. What's a code? Well, if all this thing understands is 1s and 0s, how do I send A up here to that display? Go ahead. We have to represent it with a code, right? You understand? So we got a binary code that we use to represent things. The code will look that's used in predominantly so a code is when you use one thing to represent something else, right? So the primary codes we'll look at a code called the American Standard Code for Information Interchange. Most people call it ASCII, which is right. And then we're going to use we're going to show you Unicode, which is the code used on the internet and used by all your word processors to represent other things besides numbers. And then we'll look at a code called a gray code, which is a counting code, which are still used by PLCs. Unicode, EBCDEC, the computer talks about EBCDEC. EBCDEC hadn't been around since COBOL, the programming language. You ever heard of COBOL, Common Oriented Business? It's a dead language, so we're not going to look at EBCDEC. And he don't know EBCDEC either, so we're okay. But ASCII, Unicode, and of course gray code, which I don't have up here. We need to look at that because these are codes that so this is what people don't understand. So an exponent is a number written above and to the right of another number. The bottom number we call the what, the base, and the other number we call it the exponent. The number of times the base is multiplied by itself. So 8 to the 5th would be 8 times 8 times 8 times 8 times 8. You understand that? Everybody okay? Scientific notation, this is the way that scientists and engineers easily handle very large and very small numbers. This is written in the formula of something times 10 to the nth power. Are we okay there? We use what we call engineer notation. What does that mean? We move in what groups of threes? And on the positive side of the line, we go units. Then we go what? K. What's next? Meg. What's next? Gig. Right. On the right-hand side, we go milli, micro, nano, pico. Good. That's all. So we need to understand this. Everybody okay there? Yes, yes. Rounding. Rounding is where we have the biggest problem. People, I would say round to the nearest 2 digits, and people think that means you can drop the fraction. And that's what it don't mean. So what's the rule of rounding? 5 and above, you round up. The next lower number, 5 or above, you round up. 4 and below, you round down, right? Everybody okay there? So this is what we know, right? Everybody okay? Of course, on our mass storage devices, especially hard drives, we're aware to tera. This is base 10. 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, and we use engineer notation. On the other side, we have watts. Now, this is what's nice about engineer notation. We don't worry about this, right? We don't have to worry about that. So we jump from where? We jump from here to where? Here, right? Over here, we don't worry about deca, we don't worry about cena, we go directly to what? Milli, right? So that would be scientific notation, but engineer notation means we move in groups of what? 3. Are we okay? This should be a review. So decimal numbering system is called a base 10 numbering system. Now, how did y'all learn decimal numbers? So let's just put a decimal number. So what did you learn to call that number right there that occupies that spot? What did you call that number right there? Tens. What did you call this number right here? Hundreds. And what did you call that number right there? Thousands. That's not the way it goes. That's the way you learned it, but that's not the way it goes. If you learn this, you can know any numbering system. The way a system is set up, and this is why it's called a base 10, is that we use exponents. We know that decimal has 10 digits available, 0 through what? 9. Okay. So if I was to write this number down, 5, 2, 0, 1. This guy right here actually holds a weight of 0, that number times 10 to the 0 power. This holds a weight of 10 to the first. This would be 10 to the second. This would be 10 to the third. What would the next one be? 10 to the fourth. Of course, any number raised to the 0 power is it's 1. Any number raised to 0 power is 1. You can take your calculator out and take 10,000 raised to the 0 power, and you come and say what? 1. 10 raised to the first power would be equal to what? Oh, y'all don't believe me? Y'all gonna do that? So any number raised to the 0 power is what? 1. 10 to the first would be 10. 10 to the second would be 100. 10 to the third would be 1,000. 10 to the fourth would be 10,000. What would the next one be if I put another digit out here? 10 to the fifth, right? Right? You okay? And this is why it's called a base 10 numbering system, because the base is 10. Everybody understand that? So if I did this in positional notation, let's say I put a 3 out here. In positional notation, I'd say 3 times 10 to the 5th plus 5 times 10 to the 4th plus 1 times 10 to the 3rd plus 2 times 10 to the 1st. Did I skip one? I skipped the second one over here somewhere. Oh, it's a 0 anyway. It don't make any difference. 5 times 10 to the 0. 5 plus 5. Okay. Now follow me so far. I just skipped 2, but it's a 0 anyway. So if I did this and added them all together, I would come up and get this number right there. Okay, y'all understand that? So this is the way all numbering systems, I don't care what it is, this is the way all numbering systems work. So the base, the radix, power is the exponents. Are we okay there? Okay, these are powers of 10s. Y'all know that already. This is what I just showed y'all, which is good. This would be the fractional component. So the fractional side, we take the base and raise it to a negative power. So 8.812 would be 8 times 10 raised to the what? Minus 1. The next one would be what? To the minus 2, to the minus 3, to the minus 4, to the minus 5. Everybody understand that? Okay. We okay? All right. Now, real numbers have weight that are both positive and negative powers of 10s. And they can also have a fractional component. So they have an integer. So an integer would be the whole number part, and the fractional number would be a fraction. These are called real numbers. Everybody okay? Now the problem is RS Logic 5000 calls these floating point numbers, but all your other PLCs call them real numbers. So I don't know why they did that. Are we okay? Lost anybody so far? Digits to the left of the decimal point represent the integer number. Digits to the right of the decimal point represent the fraction. Are we okay? I know y'all getting ready to go home. Integers, these are whole numbers, have weights that are positive powers of 10s. They can be positive or negative numbers. But they don't, the integer does not have a fraction, right? And we really need to understand this because binary is weird when it starts dealing with signed numbers. Because you got to be able to represent a sign without a sign. You got to be able to represent a positive and negative number with a binary, right? Understand that. So there's no such thing as a plus sign in binary. Number system. A number system is writing numbers or expressing numbers. Mathematical notation for representing numbers. Number systems used by PLCs. Of course, decimal. The PLC does not know what decimal is, but your application program does. And your application program will take a decimal number and convert it to binary for you. But it's real nice. It means a lot of my numbers I can enter in decimal. Everybody understand that? Yeah, computers process information. So what you see up here is nothing but 1 and 0. But it makes it look like what? A parentheses. Binary, octal, and then hexadecimal. Now, why we're going to deal with the octal and hexadecimal is that these are going to be able to, we're going to use these to represent binary numbers. Because binary numbers become very, very common numbers. So if I was trying to send you a binary number that looked like this, and I said, okay, and I gave you all a certain amount of time to write that down, how many would get that right? Well, what if I gave you to you like this? B5, I don't know, I did it, same thing. 7. How many of you wrote that down right? Huh? All of you. Oh, the binary or the yeah. But that's so. What we're going to find out is hexadecimal. We're not going to learn a lot about. We're going to learn how to go between binary and hexadecimal. Y'all saw I did that where I did it without even thinking about it. So a lot of the information that the PLC is going to display to you, they're going to do it in a number system called hexadecimal. Your computer even does that. So I'm going to come up here and I'm going to go to programs, and I'm going to go to system tools. Oh, I'm sorry. It's probably in accessories. Let's go to accessories. Yeah. And then I'm going to have to find it now. Oh, system tools. There it is. And then I'm going to go to system information. So this is available to you. Then I'm going to look at hardware resources. And this thing is trying to give me binary information, but instead of it displaying it in binary, it's going to use another base. Because binary would be very, very hardware resources, memory. So here's all the I/O addresses. So everything in the computer is assigned an address. And these are the I/O addresses. And you can see they look kind of weird. 3C, 3A, 2C, 2, and these are binary addresses, A0, but it's giving them to the base that makes it easy for them. But everything in the computer is assigned an address, right? You understand that? The PLC, if a computer needs to communicate with something, and if I did machine language program, I have to know all this. I'd have to know the address of the display. I'd have to know the address of the printer port. I'd have to know the address of everything. But using a high-level language that's matched to an operating system, all I do is just point at a printer. Right? But can you see, look at them? Let me show you all the memory. So this is the memory addresses right here. It really looks a bit weird, right? F1C, FFFFF. Memory address. It's a binary address, but the computer's displaying it in a numbering system that I could convert that in a heartbeat. I could see the binary address. So what we're going to learn octal for and what we're going to learn hexadecimal for is how we can represent extremely large binary numbers and make them real easy to translate. And octal was the first numbering system besides decimal used in PLCs. So just about all your PLCs still support it, even though in computers, octal is not used anymore. So the two primary number systems, the primary numbering systems they use in computers to display information to you is decimal and hexadecimal. These are two terms we need to know: fixed point numbers and floating point numbers. Do y'all understand those? So cash registers use fixed point numbers. So they always do everything to 2 decimal points. Right? But your calculators, you can set them up to do fixed points. I do that all the time to round. So if I want to round to do decimal points, I fix the decimal point and it automatically rounds for me. A floating point number is a number where the decimal point is moved. So money is a fixed point. Money you always have what? Dollars and cents. And the decimal point don't do what? It don't move. You ever work with a cash register? You start over here, even if you're programming the time on a microwave. You start entering 0. So microwaves use 6 points, right? And what does it do? This point stays and it does a lot, moves across it. So those 6 point numbers. Floating point numbers would be what most of your calculator uses. But the point can actually do what? It can move inside the number. So you'll understand floating point and then 6 points. The processor in a computer only understands numbers and codes represented with binary. All images displayed on a computer are a series of dots that are either on or off. And they use groups of 3 colors. What's the 3 colors? Oh, 4 colors. Anybody know 4 colors? Red, green, blue, black. So normally what we do is we have a black background, and then we turn on red, green, blue dots. So this last time I'll show y'all the joke. I want to look at the display on my computer with a microscope. Huh? Yeah, come up here, let's look at this. So what color is this? White. Now look through this. So it either turn you. Yeah, so all it does is 1 and 0. It either turns them on or does what? Turns them off. It combines red, so if you got more red dots will be on with a picture. So you know what this pixel is. It's a picture element. So a picture element is made up of a certain number of what we call triads. That would be a group of red, green, blue. And then you combine them to do colors, right? You understand? And that's what they call a pixel resolution. I know y'all, right now our TVs are doing what? 1080 by, those are pixels. You know, most of your computers, you can change the pixel resolution. You can actually put more triads within the square. And of course, the picture gets a little more grainy, but you use a lot less, and your computer runs faster. So the higher the pixel resolution you have, the slower your computer's going to run. So it's got to update all those pixels to update the screen. So, see y'all when? Oh, Monday's a holiday, guys. Yeah, you ought to be sitting out here by yourselves. Yeah, you